All right. I think the previous stream was either not working or there was some issue. Anyway, let me know if you're online. I'm going to wait for a couple more minutes and then I'm going to start the topic. Okay, I'll just begin. So I've posted a few videos for you to check out on the same topic. The reason I want to try to explain it from the book's perspective as well, because your primary document is still the book and you're going to follow it. So I want to make sure that you understand what's being said in the book. You can of course look at the other videos as well. I want you to look at the other videos because I'll be using them as reference material whenever I make any assignment or we have any sort of assessment. Okay, so linear transformations. Let's start off with the definitions. And so I'll just zoom out here. Hopefully this is all visible and my audio is also clear. Okay, so a linear transformation is the following. We say, let's suppose you have a vector space V and you have another vector space W. Now the idea is that there are some vectors in V, V1, V2, V3, and let's suppose there are some vectors in W. And the idea is that a linear transformation is of the following form. If let's suppose you take a vector in this space and map it onto any other vector in this space. So let's suppose V3 was mapped onto W3 or W2 or W1. And the way we write this, we call this mapping L. So this is like a function, but we call it a linear transformation. We call it linear for the following reasons. The idea is if you take a linear combination, let's suppose I had a linear combination alpha V1 plus beta V2. This was a linear combination of vectors in V space. Linear combination of vectors in V space, and what I'm going to do is I'm going to apply the transformation L on this linear combination. So now the input is a linear combination in vector space V, and the output L of this whole thing, this now entire thing, so alpha V1 plus beta V2, this was in V, but now this output is in W. And I will call this a linear transformation if and only if this output is equal to another linear combination with the same coefficients, alpha L V1 plus beta L V2. This statement is saying that if you take a linear combination of vectors in V space, and if you apply transformation L on this linear combination, the result will actually be a linear combination of the image of V1 as in W and the image of V2 in W. So LV1 is perhaps, if I take this vector would be L of V1, this is in space W. If I take this and map it onto something, this would be L of V2, which is also in W. And the idea is when you transform, if your mapping transforms a linear combination into another linear combination, so there was another vector, let's suppose over here, which was alpha V1 plus beta V2. So you take a linear combination of these two vectors, and if you try to map it now using L, it will get mapped onto the linear combinations of these two. So this would now be alpha L of V1 plus beta L of V2. And that's the idea behind a linear transformation, in that it takes a linear combination in V space and gives you another linear combination in W space. Let's look at a few examples. Okay, if L is a linear transformation mapping a vector space V into vector space W, then it follows from one that addition, we can break this down basically. Over here, we've written the whole thing, linear combination gives us a linear combination, but you can actually break it down into two steps. The first thing that we want from a linear transformation is that addition of vectors in the original space should map onto addition of vectors in the output space. And the second thing we want is that a scalar multiple of the vector in my V space of my input space should be mapped onto a scalar multiple of the image of that same vector in the output space. So, and if you combine both of these together, you get this property of having a linear combination, because a linear combination is nothing but just scalar multiplication and then addition. So this is breaking this down into two parts. Right, so that's the addition part, this is the scalar multiplication part. A bit of notation, a mapping L from a vector space V onto a vector space W will be denoted, L takes vectors from V to the vector space W. So this is a notation for your linear transformations. In the case that the vector spaces V and W are the same, we will refer to a linear transformation as a linear operator. So if you have L that takes vectors from the same space into some other vector, not necessarily the same vector, but some other vector but in the same space. So let's suppose I have V, and this linear transformation, you can draw it like this, that same space V duplicated over here, and vector V1 is being mapped onto some other vector, V2, V beta, whatever. But these need not be the same. V1 might have some other image, pre-image, or maybe it doesn't have any pre-image at all. Or you can perhaps denote a linear operator visually like this. So if you have this space V, L takes one vector from this space and maps it onto another vector on the same space. So that's a linear operator. Okay, I will try to fix my voice. Let me see. Let's see if something can be done. Okay, seems that it is full. Are you let me, maybe I can hold the mic a bit closer. Can you hear me now? Is it better now, Abdullah? Okay, I'm going to assume that worked and I'm going to move on. Hopefully you can hear me. Okay, so let's try a few examples. The first example we have here is from the vector space R2, which is the two-dimensional Alright, thank you Danya for letting me know. So that's your two-dimensional real space. This linear transformation takes the vector x and maps it onto 3 times x. And what we have to check firstly, of course, is whether this is a linear transformation or not. And the way to do that is simple. We check whether an addition stays an addition and whether a scalar multiplication stays a scalar multiplication. So if I take, let's suppose, I want to show that L of x equals to 3 times x is a linear transformation, then I need to show the following. The first thing that I need to show is that a scalar multiplication stays a scalar multiplication. So if I say L of alpha x, then that's simply 3 times alpha x. I'm just using the linear transformation rule that if you have any vector, you multiply it with 3. So I wanted to find the linear transformation of this, I just multiplied by 3. And now I can switch this because this is just algebra. Then you can switch these two and you can write this as alpha 3 times x, which of course 3 times x is nothing but alpha times the image of x. And so you have that the scalar multiplication stays a scalar multiplication. That's the first criteria. The second criteria is L times v1 plus v2. Note that x over here was the vector. Now my vectors are v1 and v2. Let's try this again. Map this. All you need to do is multiply it by 3v1 plus v2. Because this is simply now algebra, you can distribute 3 on both of them, so that's 3v1 plus 3v2, and then you can just simply write this as 3 times the image of v1 under L plus 3 times, that was supposed to be a1 and this is a vector, plus 3 times the image of v2 in L. So then you have that the addition stays as an addition. Sorry, there won't be any 3's over here. Let me write this again. This is simply L of v1 plus L of v2, and that's the correct form. So we've just shown that this transformation L of x equals to 3x is a linear transformation because of these two conditions. They hold. Of course, a direct way of doing it is to just do it directly. Instead of taking linear scalar multiplication and addition separately, I could have easily done L of alpha V1 plus beta V2, and now I can show that this is 3 times alpha V1 plus beta V2, multiply this 3 alpha V1 plus 3 beta V2, switch the alphas and 3, so 3V1, we switch the coefficients, plus beta times 3V2. And now I can just replace this bit because this is simply L of V1 and this is simply L of V2. And so you've shown that a linear combination stays a linear combination, and therefore Lx equals to 3 times x is a linear transformation. This was a very simple exercise, of course a very simple example, because if you think about it, if you are in R2, this is your R2 space, and if you had a vector, let's suppose 1, 2, so now this vector looks nothing but this is my vector 1, 2, let's suppose this was 1, this is 2, and if I find its transform, then that's just L of x is equals to 3 times 1, 2, which is simply 3 and 6, which I can draw here roughly something like this. This is the vector 3x. So this transformation is nothing but a stretching of the vectors in R2. So L of x equals to 3x stretches the vectors in R2. And actually, if you want to be more precise, L of x is actually a linear operator because it's taking vectors in R2 and it's mapping them onto vectors in R2, right? Okay, that's a simple example. We can check out another example. For example, consider this new example. L of x equals x1 e times 1. So if L of x, I have another transformation. L of x is equals to x1 e1, where recall that, let me check, this was it, right? Okay. Recall that e1 was the vector, the standard vector 1, 0. This was e1. So let's try to understand what this vector does. Let's take an example. If x was equals to 1, 2, then L of x is actually where this is x1 and this is x2, then all L of x will do, it will take the first element and multiply it with the standard vector 1, 0. So take the first one, multiply it by 1, 0. And what we get is simply 1, 0. Let's try another vector, x equals to 2, 4. If I transform this vector, then I get the first component is 2 times e1, which is 1, 0. So this becomes 2, 0. So if you notice, what it's doing is it takes every vector, takes the first component as it is, and the second component becomes 0. Similarly over here, first component as it is, second component becomes 0. We can try it out for any random x1, x2. Notice what happens, Lx equals to x1, 1, 0. What you get is x1, 0. So any vector x1, x2 is mapped onto x1, 0. And now we can of course ask the same question, is this a linear transformation? That is, if I had a linear combination of vectors in R2, will it stay a linear combination? Let's check it out. Should be easy to do. Okay, so let's suppose Lx was equals to x1 e1, and I'm going to do this directly now instead of checking scalar multiplication and addition separately. If you want to do it separately, it's available in the book. I want to do it directly. So what I want to do, I want to show the following. I want to show that a linear combination alpha v1 plus alpha v2 stays a linear transformation alpha L of v1 plus alpha L of v2. Okay, instead of taking v1 and v2, I'm going to replace them a bit by x and y. I'm just replacing the variables because I think that would make it a bit easier to understand. So alpha L of y. So first, let's make sure we understand what this term and what this term means. If I have x as the vector x1, x2, then I know that L of x is going to be just x1, 0. And if I have a vector y, y1, y2, then the transformation of that vector will simply be y1, 0, right? This is just applying the transformation individually. And now I want to show this. So let's take a linear combination of these two vectors. Let's say I'm taking L alpha x1 plus, L alpha x plus, let's make this beta. Let's make this beta, let's make this beta. Okay, so beta times y. So what would this look like? First, let's understand what's the linear combination of these two vectors. If I take alpha x plus beta y, then it's simply alpha. So L of, I'm just writing this as it is, and I'm just trying to figure out what's inside this bracket. So this is alpha x1, x2 plus beta y1, y2. And then this becomes L of, if I compute this vector, this is just alpha x1, alpha x2 plus beta y1, beta y2. And now if I add them together, they're simply, the first component is alpha x1 plus beta y1, and the second component is alpha x2 plus beta y2. And now the input is in the form of just one vector. The first component is this, the second component is this, and I'm ready to apply the linear transformation L on this. And the linear transformation was simply that you keep the first component and you discard the second component and replace it by 0. So my output will be follows: alpha x1 plus beta y1, and the second component is 0. Now I want to show that this is the same as this, so I can break it down, this entire vector, as follows. I can say, well, this is nothing but alpha x1, 0, separate this, and beta y1, 0. So I took the first component, there was an addition happening over here, and it works for the first component and it also works for the second component because the second component is simply 0. So 0 plus 0 will give you 0, and alpha x1 plus beta y1 will give you this. And now I can take alpha outside. I can say this was simply alpha x1, 0, because alpha times x1 is alpha x1 and alpha times 0 is 0. I'm still good. I can take beta outside as well, taking common, and so this becomes beta times y1. And since I've established that x1, 0 is simply L of x and y1, 0 is simply L of y, then I can write this is equals to alpha L of x plus beta L of y. And so a linear the transformation of a linear combination remains a linear combination with the same coefficients, and therefore L of x equals x1 e1 is a linear transformation. Hopefully that made sense. Okay. So let's move on. Let's actually, before moving on, let's consider what this operator is actually doing. So what it does is if you have a vector, let's suppose again, we were considering x equals to 2, 4, and its image L of x was simply 2, 0, then what's happening is, if I draw it visually, then the vector 2, 4 became simply 2, 0. So this is the image of 2, 0, this is L of 2, 0, sorry, 2, 4, which is basically 2, 0. And this vector is 2, 4. So what's happening is, whatever vector you have, its y component gets removed, and you have a flat vector that's on the x coordinate, or rather on the x-axis. So for example, if you had a vector like this, its linear transformation will be something like this. So its vertical component will die away, and you will have just the horizontal vector. So what, if you think about it, what L of x equals x1 e1 is doing is, yes, it's taking vectors from R2 and mapping them on R2, but it's not mapping them entirely on R2. It's only the image. You can say that the resulting vectors of this transformation lie entirely on the x-axis. So that's important to note, that it's possible that your entire space is not being covered. Your image, whatever your linear transformation was, maybe it's just covering part of that vector space instead of covering the entire vector space. So you had vectors entirely from R2, and they were just mapped onto vectors in only on the x-axis of R2. So if you think about it, the image of 2, 4 is L of x is simply 2, 0. But if you have any other vector, 2, 30 even, the image of that is also going to be 2, 0, which tells you something. So just like functions, the image of this linear transformation is not unique. So in some sense, this transformation is not one-to-one, because both of these inputs have the same outputs, they have the same image. Okay, let's move on. Okay, you have another operator. This operator is, what's it doing? It's taking the first component as it is, but the second component is being multiplied with a negative sign. And you can show, using the same arguments, that this is a linear transformation as well. You take the linear transformation of a combination, alpha x plus beta y. First component is as it is. Second component gets multiplied with a negative sign. You can write this addition as this, separate them into two vectors. If you want to check that this is the same, this line is the same as this line, try multiplying the coefficients and adding them together. So the first component will be alpha times x1 plus beta times y1, which is this. And the second component will be negative alpha x2 plus negative beta y2, and you can take the negative common to get this line. So this is the same as this, and this part is just the transform of x, this is just the transform of y, and you have the same linear combination on the right hand side. So this is also a linear transformation. And what this does is just, if you have x1, x2, it gets mapped onto x1 minus x2. So it's sort of a reflection about the x-axis. And if your vector was already below the x-axis, it will get mapped onto the top part. So now this transformation, unlike the previous one, will cover the entire R2 space. because each vector gets mapped onto its image on the other side. So if the first half plane will be mapped onto the lower half plane, and the lower half plane will be entirely mapped onto the upper half plane. So your entire R2 space will be covered. You can, example 4 is another variation. What does it do? It flips the coordinates and it also adds a negative sign. And it's easy to check that it's a linear combination. And the overall effect of this combination, you can try mapping it, and perhaps we can see what's going on by trying out a few examples. Where did my, yeah, here it is. So let's try this out to see what's exactly going on. And so L of x is simply minus x2 and x1 transpose. So let's try a few examples. If x is equals to 1, 2, it gets mapped onto the output L. L of x is simply minus of x2, which is 2, minus 2, and x1, which is 1. Similarly, if x was 0, 5, then this becomes L of x becomes minus 5, 0. And let's call this x. So let's call this x star. Let's see what's happening to these two vectors. So the first vector, if I draw this in the xy plane, the first vector was 1, 2, so 1, 2, it gets, and the image of that vector is minus 2, 1. So minus 2, we have minus 2 and 1, it gets mapped like this. If I have another vector 0, 5, so 0, 5 will be here. 1, 2, 3, 4, 5. So this was my vector 0, 5. And if I draw its image minus 5, 0, it's going to be like this. So that's minus 5, 0. So this vector got mapped onto this one, and this vector got mapped onto this one, and what's happening, if you notice, is you're getting a 90-degree rotation in the clockwise direction. And that's happening because both of the coordinates are being shifted and one of them is getting a negative sign. I want you to think about the following. Think of a linear transformation for the following. A 90-degree, this was, by the way, I was wrong, this was not clockwise, this was anti-clockwise. I want you to think about a transformation that would give me a 90-degree clockwise rotation and a reflection. These are separate. And I also want you to think about how you can get a reflection in the y-axis. This should be easy. This should also be easy. Try out a few examples. Try putting a negative sign here, try putting a negative sign here, or maybe on both sides, and see what you get. Okay. So those were a few examples. Let's check out what else. Okay, now we have our first example of a linear transformation that is going from one space to another space. So this transformation is going from R2, it's taking a vector and it's mapping it onto a scalar because it's in R1, so it's just a number. And the way it's doing that is by just adding the two components of the vector. So if my vector x was x1 and x2, it's just adding the two components and that's the result. So for example, if I have the vector, now I have a new transformation, L of x equals x1 plus x2. Then what's happening is if I have the vector 1, 2, then the linear transformation of that vector is simply 1 plus 2, which is 3. And this is of course in R1, and the input was in R2. The output is just a number, the input is a vector of two components. And again, you can check that this is indeed a linear transformation. Perhaps we can try doing that. Let's take alpha x plus beta y, and this will be equals to, so I will have the first component added with the second component. So the first component of the input will look something like this. Let's write it down. When I write it as a vector, this will be alpha x1 plus beta y1, just as we did it in the previous exercise, plus beta y2. Sorry, these are not vectors, these are numbers now, these are not vectors. And now, what will L do? L will just add these two components together because that's the transformation that we have. Take the first component, add it to the second component. So we took a linear combination and now we're applying the linear transformation on it. So alpha x1 plus beta y1, and add this to alpha x2 plus beta y2. And to show this is a linear combination, at the end, my end goal of course is to show that this is simply alpha times L of x plus beta times L of y, which is simple to see because L of x is simply going to be x1 plus x2. Let's do that. Let's rearrange these terms. This becomes alpha x1 plus alpha x2 plus beta y1 plus beta y2. Take alpha common, I get x1 plus x2, and take beta common, I get y1 plus y2. And notice that x1 plus x2 is nothing but the linear transformation of x, and y1 plus y2 is nothing but the linear transformation of y, using this property, using this transformation, the original transformation. And so I can replace this with L of x, this with L of y, and I have shown that a linear combination stays a linear combination. But this time the transformation was going from the vector space R2 to R1. Okay. Here's our first example of a transformation that is not linear. So M of x is a transformation that squares both of the components and then takes the square root. And if you recall this, this is nothing but the Euclidean distance of, sorry, the Euclidean, the size of the vector. So if you want to know the magnitude of the vector M of x, perhaps that's why they've denoted it with M of x, is that it just tells you the magnitude. And so the magnitude is also a transformation, because what it does is it takes your vector was perhaps x1 and x2, and then M of x takes this vector and makes it x1 plus x2, square them together, square them separately, and then place a square root on them, which is basically if you x1 squared plus x2 squared. And now of course this is in R1, this is just a number, but this was a vector. So M is a transformation from R2 to R1, but it's not linear. And the reason it's not linear is because a linear transformation, a linear combination will not stay a linear combination. Let's see how they've shown it in the book. So we took a linear combination alpha x1, alpha x2, and if you try to square them and put a square root, you can show that this side is different than the right hand side. Perhaps if we write them separately and check it out for ourselves. So let's say I had alpha x plus beta y. Then I can check, actually instead of doing that, what we can do is we can just show the part that is scalar multiplication. Instead of showing the whole thing, just show that the scalar multiplication doesn't stay, just like they did in the book. So the scalar multiplication of alpha x is going to be m of alpha x1, alpha x2. And now to apply the transformation on it, we have alpha x1 whole squared plus alpha x2 whole squared and then square root on this. And you get square root alpha squared x1 squared plus alpha squared x2 squared, and you get alpha square root, am I doing this correctly? Yes. So alpha squared x1 squared plus x2 squared, and this should give you alpha. Wait, what? What am I doing incorrectly? Yeah. So you get square root over here and you get x1 squared plus x2 squared. Now the square root of a square is not going to cancel, it's actually equal. We have to be precise here, so it's actually not equal to, you can't cancel these two. What you have is actually the absolute value. The definition, the definition of the absolute value is you square a number and square root is. So absolute value of alpha will not be the same as alpha itself, because if you think about it, if I had taken alpha to be a negative number, the negative number would have become squared here, and when I apply square on it, it becomes positive. So inside the square root, this number has become positive, and once you apply the square root on it, this is a positive number now. So essentially we have my L of alpha x has become the absolute value of alpha times L of x. But what I wanted was that the scalar multiplication should just remain a scalar multiplication. And so the difference is that over here I have the absolute value, but over here I have the actual scalar multiple that I started off with. So if this number is negative, these results won't be the same, and so I do not have this property, and therefore, well, this was m, so m of x is not a linear transformation. So we've got to be careful, and I keep making this mistake myself, but remember that square root of alpha square is not the same as alpha. It's actually equals to the absolute value of alpha. Okay. So that was an example of a transformation that is not a linear transformation. Okay, let's check out another transformation that takes vectors from the two-dimensional space to a three-dimensional space. And the way it does this is it flips the first two coordinates, and for the third coordinate it just puts an addition on. So it just adds up the two components. So as an example of this transformation, let's suppose, so we have the transformation L of what was it? L of x is simply x1, sorry, x2, x1, this is 2, and x1 plus x2 transpose. So essentially what it does is if you have a vector 1 by 2, then the image L of x is going to be equals to a three-dimensional vector where the first component is x2, which is 2, the second component is x1, which is 1, and the third component is the sum of these two components, 1 plus 2, which becomes 2, 1, 3. So the image of 1, 2 under this transformation is 2, 1, 3. Okay, you can try out different examples, but of course we are interested in showing that L of alpha x plus beta y is equals to alpha L of x plus beta L of y. And the proof is of course in the book as well. I don't want to go through it. You're familiar with the process. I recommend that you try it out on your own. Okay. Note that if we define the matrix, this is important. Note that if we define the matrix A by 0, 1, 1, 0, 1, 1, and if we multiply a vector x with A, so this is a matrix and I'm multiplying it with x, notice that you get the same result x2, x1, x1 plus x2. Let's try that out. Let's verify this on our own. Let's check the vector. We have the matrix 0, 1, 1, 0, 1, 1. And x is, let's suppose, x1 and x2. What happens when I multiply this matrix with x? Well, I take 0, 1, 1, 0, 1, 1, and x1 and x2. I multiply it like this, multiply it like this, multiply it like this. So row by columns, I get the first component is 0 times x1 plus 1 times x2. So 1 times x2. Second row times the first column, 1 times x1 plus 0 times x2. And then finally 1 times x1 plus 1 times x2. 1 times x1 plus 1 times x2. And the result is the first component is x2, the second component is x1, and the third component is their sum, which is exactly equal to the linear transformation that we were doing right now. So in this example, they've shown that this transformation can be obtained by this matrix multiplication. And of course, this raises an important point. Why can we do this? And can we do this for all transformations? And the answer, spoiler alert, yes, you can do this. Every linear transformation. This is a theorem in the next section, but I got tempted, and so here it is. Every linear transformation can be expressed as a matrix multiplication. So for any linear transformation, there exists a corresponding matrix with which if you multiply your matrix with the vector, it will give you the same result as the linear transformation that we were doing. And once that's true, you have all of the machinery. You can use all the results of matrix vector multiplication or matrix algebra on linear transformations, and that's readily available to you. We've already spent quite a lot of time in this course talking about matrices and multiplication and matrix algebra, and we see that linear transformations can easily be represented as matrix multiplication. Well, we haven't seen that in detail, but that's the topic for the next section. Okay. All right, so now let's talk about a general linear transformation. So what about a vector space V to vector space W? if L is a, of course, now we're generalizing it because R2 and R3 are specific vector spaces that we like because they're convenient to work with, but you have other general vector spaces as well. For example, your vectors can be matrices, your vectors can be functions, your vectors can be continuous functions or polynomials, different examples that we've done. And so for those general cases, here's a description of what will happen if you have a vector space V and you're transforming it using a linear transformation and mapping it onto a vector space W. So these three properties should hold. The first property is the zero vector in your vector space, in your input space, should be mapped onto the zero vector on your output vector space. So that's the first condition. That let's suppose we had this vector space V, and let's suppose we had this vector space W. L is a linear transformation if and only if it takes the zero vector here, this is the zero vector of the V space, and let's suppose there's a zero vector in this W space. If it's a linear transformation, then you're guaranteed that this 0 is going to be mapped onto this 0. There's no other ways about it. And the way we know this is just consider the property of a linear transformation. L of alpha x is simply L of x. Notice that this little thing is in the V space. The input is in V space, and the output is in W space. And so let's check it out. If I set alpha to be 0, the coefficient can be anything. And we know that if you multiply the 0 coefficient with any vector, we know this for sure, that for any vector space, 0 V is simply equals to the 0 vector in my space. These two zeros are different. Please make sure that you know what I'm talking about. This 0 is a real number, and this 0 is the 0 vector of my vector space V. It's not underlined. Okay. So L of the 0 vector in V space is equals to 0 times this. So 0 times L of x. It doesn't matter whatever this vector is, it's going to multiply it with 0 and you get the 0 in the W space. So L of 0V is 0 in the W space. That's the first property. The second property is that if you have these vectors in V and alphas are your scalars, then the linear combinations will stay a linear combination. That's something that we've already discussed. And finally, if you have negative of V, then it just goes outside. This is easy to prove because this is, you can just prove it using alpha equals -1. So this is simple to prove, but what's important to notice here is that this is actually negative of V is the additive inverse. Notice that for vector space V, if the small vector V belongs to V, then there exists the additive inverse in V such that if you add vector V to its additive inverse, the result is going to be the 0 vector. And so what you've shown is the following, is that the additive inverse of the vector is mapped onto the additive inverse of the image of the vector. So that's also important to note, that let's suppose you had a vector V and this was mapped onto L of V. Now of course this is a vector space, so additive inverse exists. So the additive inverse of this is going to be negative V. And this is a vector space W. Additive inverses exist over here as well. The additive inverse of this one would be negative L of V. And by linear transformation, I'm guaranteed that this is going to map onto this. That the additive inverses will also map onto each other. So that's a nice little property of linear transformations. Okay, you have an example of a very specific linear operator, which is the identity operator. And the identity operator does nothing. It just takes the vector and outputs it. It does nothing on it. So the identity vector takes v and outputs v. And it's an important vector when you can prove that it's of course a linear transformation, a linear operator. It takes a vector from the same vector space and puts it in the same vector space. It's a very trivial linear operator. Okay. Of course, like I said, we're not limited to just vectors in R2, vectors in R3. We can have functions as well. So now there's an interesting linear operator that I want, not a linear operator, a linear transformation that I want you to see. Okay. So we have a transformation that takes vectors from this space CAB, and recall what this space was. This was the space of continuous functions defined on the interval, the closed interval AB. So if you have the closed interval A to B, then every continuous function is part of this space. Every continuous function defined within these two intervals, within this interval. And this is mapped onto R by the following transformation. It takes a function f of x and it outputs the definite integral a to b f of x dx. And of course you should know by calculus that this is just a number in R1. So it took a function and the output is simply R1. So what you've done is you've redefined integration as a linear transformation. So integration is nothing, but it takes vectors from this space and gives you vectors in this space. And in light of that, we can now show that, of course, a integration is a linear transformation, and the way you do this is by taking a linear combination of a function fx plus another function gx, and if I integrate it from a to b, alpha fx plus beta gx dx, then you know by basic integration rules that you can separate these integrals. You can write this as alpha a to b f of x, alpha is a constant dx, plus beta a to b gx dx. And what you've managed to do is you've written this as alpha L of f of x plus beta L of g of x. So a linear combination stays a linear combination. A linear combination of functions has now become a linear combination of these two numbers, basically the integral. And so the integration, the definite integration of continuous functions, this is important, your space needs to be continuous, of continuous functions is a linear transformation. So you're seeing another concept of calculus, but described in the language of linear algebra. Okay. You have another example. Let D be the linear transformation mapping continuous and differentiable C1 functions. So C1 functions are those functions which can be differentiated once. And they are being mapped onto a class of continuous functions. So you've differentiated them once. So now they're just continuous. And you've defined it by just taking the derivative. And again, using the properties of derivatives, you can show that D is a linear transformation. Okay. see how much time has passed. All right. Just going to take a little bit of break from talking. All right. So the next idea is that of an image and a kernel. What does an image and kernel mean? Let's consider let's go back to the idea of vector spaces. So we had the vector space V and we had the vector space W. Okay, we have two important subspaces to look at as far as linear transformations is concerned. The first important thing is we know that it's possible that this mapping may not be one-to-one. So many vectors from this space can map onto the same vector in this space. And the vector that we're interested in is the zero vector in the output space. And the question is, how many vectors in this space map onto the zero vector in the output space? And that space is called, all of these vectors, the collection of these vectors is called the kernel of the linear transformation L. So let L from V to W be a linear transformation. The kernel of L, denoted ker L, is defined by the kernel of L is equals to every vector. It's a collection. Notice that this is a set notation, so this is a collection. It contains every vector V such that L of V is 0. So all of these vectors, these are part of the kernel space, which is denoted as kernel L. So let's suppose V1, V2 were the vectors, so kernel of L can be a collection, suppose V1, V2, and all the vectors that map to this zero vector. Okay, and the second concept that we're interested in is the image. Let's suppose we had a subspace. Recall that we've already covered the concept of a subspace. If you don't remember it, let me remind you that a subspace is nothing but a subset that is also a vector space. So it should satisfy the vector space properties. So let's suppose you had this subspace S in your vector space V. The question is, what's going to be the image? We call this, let's suppose we take this entire collection vectors from this space and map them onto vectors in this space, and let's suppose we get another collection over here. Let's call this and we call this collection the image of S under L, right? And so let L be the linear transformation and S be a subspace. The image of S denoted LS, so we denoted using the notation LS, and it's the collection of all of the vectors that were the image of the subspace. So this space, by the way, this is called the image. Notice that kernel contained vectors from my original space. In image, we are interested in not these vectors, but these vectors, W1, W2. All of these images. So image will be, let's suppose W1, W2, W3, and so on, such that each of these W's is an image of a vector in S, such that, for example, W1 could be the transformation, the output when you transform V3 perhaps. W2 can be the transform of V2. And the important thing is that V3 and V2 should be part of the original subspace. Okay, so this was the idea of an image and this was the idea of a kernel. And the reason we care about this is the following. This theorem. It tells us that if you have a linear transformation, then both of these spaces that you've now found, that collection that you've now made, the collection over here, this collection, and this collection, we know nothing about these collections, but we have a theorem that tells us two important details. The first one tells us that the kernel is a subspace of V. Of course, it can't be a subspace of W because the collection is in V. And the image L of S is a subspace of W. So the image of a subspace also gives you a subspace, and the pre-image of the zero vector is also a subspace. And that's the important thing about kernels and images. We'll use them in computations and in proofs. Here's a proof of these two statements. I'm not going to go through them. I want you to go through this on your own and let me know if you have any confusion. This is part of the course. I want you to understand it. Don't try to skip it, and make sure that you understand it as clearly as possible. Okay. Alright, here's another example. Let L be the linear operator on R2 defined by x10. So as an example, let's see what the kernel of this space will be. Let's just do an example and then we'll end this lecture. With example 11, you can look at example 12 on your own. Okay, so here is example 11, which asks the following question. If you have the transformation Lx as x10, what's the kernel of this linear transformation? And of course, this is a linear operator from R2 to R2, and the question that we're really asking is the following: which of the vectors in R2 will be mapped to the zero vector in R2? And now if you recall, what this transformation was doing is, if you had a vector like this, it was just bringing it down to the horizontal x-axis. So if this was x, this was L of x. If, let's suppose, this was y, then this was L of y. This is just a visual representation. Let's suppose if this was z, then this is going to be the image of c, L of c. And so the question is, which of these vectors from R2, consider all the infinitely many vectors, which of them will map onto this point, just the zero vector? So I'm looking for x in R2 such that L of x is just the zero vector. And of course, this is easy to see, that if you just have a vector whose first component is 0, we don't care about the second component because the second component becomes 0 automatically. Then if you take the image of this vector in this transformation, it's going to map onto 0, 0. And what vectors are these? These vectors are nothing but, if you think about it, these vectors just lie on the vertical axis. So all of these vectors, when they don't have a horizontal part already, and if you apply this linear transformation which removes their vertical part as well, all of them, these negative ones as well, will be mapped onto the 0 vector. And so I can say that the kernel of L is actually all the vectors x in V, or sorry, in R2, such that x is equals to 0 x2. Or maybe I can write it in a different way. I can say it's all of these vectors in R2 such that x is equals to x1, x2, and x1 is simply 0. Of course, this is an infinite collection. The kernel space is an infinite collection, and what this is telling me is it's telling me that all the vectors in this space form a subspace, because I already have a theorem that tells me that the kernel space is a subspace of R2. And so all of the vectors that lie on this vertical plane, if you take a collection of them, then you get a subspace of R2. And that's it for today's lecture. I think we're done. I want you to go through these examples, the ones that I've skipped, and do the exercises as many as possible, and feel free to ask me any questions that you feel in this chapter or the previous chapter. And if you feel, and just as a preview, the next chapter, or rather the next section, is going to be about how we can take any linear transformation and express it as a matrix vector product. So this is something that I've already mentioned, but I've not gone into the details. We'll go into the details in the next class. All right, thank you. I don't think, yeah, only 3 of you are online. That's fine. You can see this video whenever you get the time. Have a good day.